Bing. All right. So just a reminder to those of y'all online, we will have a test on Friday, more than likely. There's a small chance it'll be on Thursday, but probably on Friday. So make sure that you're getting caught up on your work. Make sure that you're emailing me during school hours. Usually if you email me after like 4 or 5, it's difficult for me to email you back and get back to you. You need to be waking up early and starting on your work early, so we can email back and forth all day, because usually one email doesn't take care of it. And I'm not going to be emailing late into the night. So make sure that you're taking care of this. Those of y'all in class, if you get behind, you need to come in during activity period. And you need to be working on stuff during activity period, because these daily assignments don't count for much because we don't do a lot of them. But I think you can see that if you don't know what you're doing on the quizzes, your grade goes down pretty quickly, and the tests aren't going to be super great either. So make sure that you're kind of learning this and understand this. This is a tough year because obviously we got a lot of stuff going on. All the teachers are really busy and kind of stressed. So make sure that you're keeping up with your own business and staying on top of things, so you don't get any surprises come report card time. But we're going to start our new section today. We finished up the quiz on Friday. So we're going to get into electron arrangements. And this is actually something that is a little bit difficult until you get it. Once you get it, it makes a lot of sense, but it's not going to be super easy right off the bat. Everybody's going to need periodic tables. In fact, will you do me a favor and pass the rest of these out? I'm going to erase this with a nice clean board for everybody, because we got some stuff to go over. Now, so this is called electron configurations. We have another assignment about electron arrangements, but electron configurations is basically our way, our way to keep track of electrons and tell other people that we're working with how many electrons we have, and more importantly, where they're at and what they're doing. This is the most important thing for chemistry, because you'll see when we get into chemical bonds and chemical reactions, the protons and the neutrons don't do anything. They always stay there in the same nucleus. They hardly ever leave, unless you're talking about like radioactive elements, which are very different. But when you do a chemical reaction, when you make a new substance, all of that is the electrons. It's electrons moving around, electrons combining, sharing electrons. The electrons are what does the important chemically stuff. And so we need to know where they're at. We need to know how many we have, on what levels, and what's available for us to use. And the way you do that is electron configurations, because very quickly on here, you can get to a lot of electrons. If it only has 5 or 6, it's not that bad. If it has like 50 something or 100 something electrons, that gets kind of difficult to tell where all those electrons are. So we have different ways to do that. So we're going to start off at the beginning with the Heisenberg uncertainty principle. And this principle basically states, and we talked about this the other day, we can't know the exact velocity and the position of an electron. We can know one, but we can't know the other. That's just how it works, and the way that we have everything set up right now. Maybe one day later in the future, we can overcome this and we can figure out both of them. But right now, today, with the technology we have, as advanced as it is, and as much as we know, we at least know that we can't know this. We can't know both of these. We can know the velocity. If we know the velocity, we don't know the position. If we know the position, we don't know the velocity. So that is the Heisenberg uncertainty principle. So what we've created around this are these atomic orbitals, an area around the nucleus where electrons are likely to be found. We don't know 100% of the time that they're there, but it's pretty probable. And so it's just an admission, again, that we don't know everything about electrons and what they're doing. We've got a pretty good idea, and so we can make some estimations and get these orbitals. Now, I mentioned this before when I talked about how the planetary model of electrons, where you have a nucleus in the center, and then you have your electrons orbiting, kind of like the planets do. That's wrong. And we thought it was right for a long time, and we still teach it in school because it works pretty well and it helps us out. But we know now, because of the Heisenberg uncertainty principle, we can't know where that electron is. We can only guess at it. And so saying it's orbiting around a nucleus just isn't true. They don't orbit in circles. That's not really what they do. And so we've moved on to something else. And what we've moved on to are these atomic orbitals, or as they are referred to, electron clouds. So basically we have an area, and more than likely our electrons going to be in that area at any given point in time. Now the clouds, depending on how many electrons you have and how far away they are from the nucleus, the clouds have different shapes. They go from simple, which is just a circle. This is the simplest one. It's just an s orbital, to more and more complex. So you have p orbitals, which is like two circles put together. You have d orbitals, which can have like donut shapes. You can have four circles and different arrangements and like organizations. And then there's even one more called the f orbital, which I don't know if we have shapes for those, or if it's just too complicated, we don't even bother to draw them. But know that there are four different types: S, P, D, and F. And I'm sorry, I wish I had some words to tell you like what these mean, or maybe I wish they were in alphabetical order. They're not. You just have to remember that S is the smallest one. Then it goes to P, then it goes to D, then it goes to F. And when we actually get into it, it's going to be a little bit more confusing than that, because it doesn't always necessarily go in that order. But there is a pattern to it. And if you use the images that I give you, you should be able to follow the pattern and understand. So we're going to start off with quantum numbers. Quantum numbers is the sets of numbers used to describe properties of atomic orbitals and electrons in them. We only have a couple of these. So they describe the size, the shape, and the energy level of orbitals, and the direction of the electron spin, which is actually nice. One of the things we learned relatively recently is that electrons actually have a spin on them. They're spinning almost like you'd spin a basketball. And you can spin them one way up, or you can spin them the other way down. And depending on whether they spin up or down, they will have relations with each other in different ways. I think if they're spinning the same way, they don't really like to be next to each other. If they're spinning opposite ways, you can put them kind of close to each other, and they don't mind that. So we start off with your principal quantum number. This is actually a number. And the good news is there's only 7 of these. These numbers correspond with rows of the periodic table. And so if you find that element, you know the highest number that goes to. So like hydrogen is right here in the first row. Hydrogen's just in the first principal quantum number. You're only going to use number 1. You won't have any 2s or 3s or anything like that. So that is actually the row of the periodic table that it corresponds to. Second, so that's your principal quantum number, or your main energy level, how much energy you have. Next, actually, they're going to start off here. You get to your sublevels. The sublevels are the letters that I just mentioned. So S, P, D, or F. Those are your 4 sublevels. So those are going to go next to those. So you can have any number of your principal quantum numbers, what row you're in on the periodic table, and S, D, P, and F actually, we'll see in a second, correspond to what part of the periodic table you're in. The S column are the first 2 on the left. So you have orange and yellow right here in these 2 columns. Those are S. When you get into P, that's this square block over here with the light blue, the dark green, the light green, and then the 2 blue colors on the end. That square block is the P. The D is the purple block, or not purple, but pink block in the middle. And then F are these bottom 2 down here. So there's 4 letters. There's 4 major chunks of the periodic table. The 2 columns on the right, the square, no, it's not right. I just messed up. 2 columns on the left, the square block on the right, the pink block in the middle, and then the 2 rows on the bottom. Those are your 4 areas of the periodic table. Those are your 4 letters to go along with your 7 rows. And so that's kind of how this is going to shake out. What you want to find is your element and figure out where it's at, what row it's on, and what block it's in. That will tell you the orbital type. So hopefully they actually show you that in a second. Know that you can only have a certain number of electrons in each block. If we're talking about neutral electrons, every electron has the same number of protons, right? So how many protons does hydrogen have? Just one. So how many electrons is it probably going to have? Just a one. What about helium? 2. So it's probably going to have 2 electrons. So this is how it's going to go all the way through the periodic table. For every new element you get, you add 1 extra electron. Hydrogen has 1 electron, helium has 2, lithium has 3, beryllium has 4, and it just keeps going up on and on. So for the S sublevel, you have 2 columns, right? You have the orange one and the yellow one. There's only 2 electrons that can fit in there. They have opposite spins. We're not going to do a whole bunch with the spins, so don't get too concerned with the spins up or down. But know that the reason they can fit close together here is because they have opposite spins. So I have one spinning up, one spinning down. They can be together. That entire column has 2 electrons in it. For the P sublevel, sorry, I'm going to use this. Actually, let me get my own. For the P sublevel, how many columns are in this block over here? Going from beryllium number 5 to neon number 10.
37.
No, how many columns are there?
Oh, 6.
There's just 6 columns. So if you look at the P sublevel, how many electrons can be in there? 6 electrons. Count the pink, the top row of the pink. How many elements are in that top row of the pink? 10. So you go to the D sublevel, you have 10 electrons. There's 5 blocks here with 2 electrons each. You have 10 electrons. So how many electrons fit in each of these rows or each of these sublevels? The number of elements that block is wide. So the S block is 2 elements wide. The P block is 6 elements wide. The D block is 10 elements wide. And if you count it at the bottom, it's a little bit off because, no, this one's actually right. Yeah, the bottom one is 14 elements wide. Let me count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You'll notice down here, this 2-row thing has 15 in it. It's actually going to be 14 because I don't know if it's the first ones or the last ones. I think it's the last one. The last 2, LU and LR, they actually belong kind of up here in the D block with the pink ones. So notice they kind of have 2 missing out of the pink block. That's 2 of them are supposed to be here in these bottom 2 rows. So F is 14, not 15. Although you won't have to do that a whole bunch, and you should have some images to help you out with that. So here you go. S is going to contain 2, P is going to contain 6, D is going to contain 10, and F is going to contain 14. Now, what are we getting at with this? Why are we doing this? Why are we learning this kind of stuff? We need to make an electron configuration. It's a set of numbers and letters that describes an atom's electron arrangement. Every electron in that atom, all the way from the first to the last. That's what we want to describe. And we need to give a place for it and how many we have. So we're going to start off with a ground state one. We will give you an extra one that is a little bit easier to write about in a second, but we need to learn this one first. So what we're looking for here, they're going to go through these. Or are they just going to tell us about it? I guess we're going to go through these. We got 3 principles that we're going to talk about. Sorry, this is going to be a long lecture, but once you get to the assignment, you need to kind of understand this stuff before we just throw you into the assignment. These are going to get harder and harder as we go. This one's not too bad because there's not a lot of math, but it's basically a lot of counting and keeping up with numbers. So we have 3 rules that govern this ground state electron configuration. The first one's the off-ball principle. The second one is Pauli's exclusion principle. And the third one is the Hund's rule. So to start off, the off-ball principle states that electrons fill available orbits with the least energy first. And basically, an example of that is you come into the room, if you didn't have a seating chart and you were electrons and I was your nucleus, you would all sit in the front row first. And you wouldn't sit in the back seat until all the rows were filled up because you, as an electron, which are negative, you want to be attracted to the nucleus, which is positive. Maybe it's a bad example to have it students to teacher. Maybe we'll just say the board. As negative students, you want to be as close to the board as possible. So you're going to sit in the front row first. The next person in the room will start in the second row, and you go back and back and back. There's not going to be any empty seats towards the front. That's just not how electrons are going to do it. They're going to fill the closest available seats as possible. That's the off-ball principle. They're going to fill the front. So their example here is you go up from this bottom one, and this actually causes a problem. Some of the seats are further away than other seats. So you're not actually going to fill each of these rows in order. You're going to have, so you have 1s, and then you go 2s and 2p. So if we're going down, 1s is hydrogen and helium. 2s, everybody look and follow along with me on your periodic table because you need to get used to counting these. 1s, hydrogen and helium. See how helium's kind of on its own over there? There's nothing next to hydrogen. In reality, helium gets slid over there and sits in that spot next to hydrogen. So 1s is hydrogen and helium. Those are your first two electrons. 2s, lithium and beryllium. Those are your next two electrons. Then you get to the p block over here. Boron, carbon, nitrogen, oxygen. So you have 2p right here. Then you have 3s, sodium and magnesium. Then you go to 3p, which is aluminum through argon, the second row of the p block. Then you have 3d, which, no, you don't go to 3d yet, my bad. See, it's already getting a little confusing. Then you go to 4s, potassium, calcium. Then you go to 3d, and this is where things get a little weird. The pink block here, what's the top row? What row is that in on the periodic table? Fourth, but we don't call it 4d. That's actually 3d. And so things get a little bit messed up in the way that the periodic table works with these electron configurations. Basically, the electrons aren't sitting where it always looks like they're sitting. And so D is offset by one row, and actually F is offset by, I believe, 2 rows maybe. Yes, because the two bottom ones down here, what rows are they in on the periodic table? 6 and 7. They're not 6F and 7F. They're 4F and 5F. And so they're shifted up as far as electrons are too. The good news is you'll kind of have this progression available to you on the test and everything. You just need to know how to be able to read it and understand what you need to do. And so know that this all gets shifted a little bit, and it kind of gets wonky past the beginning. So you go 1S, 2S, 2P, 3S, 3P. Then you start into 4s, 4S, but you go back for 3D. So you have 4S, 3D, 4P. Then you have 5S and then 4D. And then once you get up here, the F's come in and they're all messed up. So you have 5P, 6S, 4F, because the F's are a little bit off on their numbers. And so don't just go like across like you're reading it. Know that the D columns or the D rows and the F rows are a little bit off and weird. We'll have a better image to kind of help you progress through this in just a second. So that is the off-ball principle. It says that everything's going to sit as close as it can to the nucleus, but it doesn't necessarily go in the order that you want it to go, or the order that your brain thinks it should go, which is one of the things that makes this super difficult. Maybe not super difficult, but more difficult than it should be. So within a single energy level, S comes before P, comes before D, comes before F. Just know that D and F don't really sit in the right place that the S and the P's do. D is off by 1 row. F is off by 2 rows. Now, here's the blocks, and this is actually going to help you out a lot. The periodic table can be divided into these blocks that match up with your orbitals. So your S block is right here, including hydrogen and helium. Those both belong in this S block. Your P block is over here. So 6 elements across, and you have 5 rows right here. Your D block is right in the middle. That's your pink elements, including LU and LR, like I said at the beginning. So your F down here is 14 and not 15. But all these go in here. And then you have your F block at the bottom with 14 elements across. So if you can remember the periodic table divided into these 4 sections, that will help you get through these problems quite a bit faster. This is actually the image that you will get to use on your test. And I'd encourage you, while you're doing this assignment, to pull up the study sheet. The study sheet will have this on here, and it will help you out. Basically, it shows how everything is divided up and how you go through each of the energy levels. And down here at the bottom, it tells you what order they go in. So notice the 3D is in between 4S and 4P, which doesn't really make sense because if you come over 4S, you actually get 3D because the Ds are shifted up one. Same thing with the Fs. The Fs are in row 6 and 7, but they're 4 and 5. And so that kind of helps you go through this progression all the way until you get where you need to go. Are they actually going to go through the other ones? Yes. So here's the Pauli exclusion principle. This states that each orbital can hold a maximum of 2 electrons. And basically, when they talk about orbitals, you're dividing the number of electrons you have by 2. So the s orbital only has 1 orbital that has 2 electrons. The p block has 3 orbitals, which each have 2 electrons, which gives you 6 electrons. The d block has 10 electrons, so it only has 5 orbitals. The f block has 14 electrons, so it only has 7 orbitals. So if they ask about an orbital, just remember that it's holds 2 electrons each. We're not going to do a lot of work on these, but there will be some sapling questions that kind of talk about that. Remember that particles with like charges repel. Your electrons are all negative. They don't want to be next to each other. Negative charges aren't going to want to sit right next to each other, especially in a small area like an atom. And so they tend to keep as far apart as possible. So when you have these electron blocks like these orbitals, you're not going to have 2 electrons sitting right next to each other when there's an empty space. Same kind of way with y'all as students. If y'all were piling in here from front to back, if you have 2 desks right next to each other, y'all aren't going to fill up those desks. If there's an empty desk, you're going to go sit in the empty desk, right? Yeah, you don't want to be like elbow room next to each other. Electrons are going to be the same way. So they're going to fill up the individual spots first, and then if they have to sit in that seat, they will come and sit in it, kind of like middle seats on an airplane. They're the last to fill up, unless, I'm thinking Southwest because other airlines, they have assigned seats. But in Southwest, where you get to pick your own seat by the time you get in the plane, aisle rows and window rows get filled up immediately. And then the last people on the plane always get the middle seat because it's the worst seat and everyone hates the middle seat. So same thing with electrons. They're not going to sit next to another electron unless they absolutely have to. There's no seat left. That's Hund's rule. Now let's see. You will not do a lot of this. They might ask you for a couple things with arrows, but you should be able to figure it out. So now we're going to get into actual electrons. So how do you write the electron configurations? First, you need to determine the highest energy or sublevel of the atom. Step 1, always with this, find the atom they're asking you about. Where is that element? Where is it on the periodic table? What row is it in? What block is it in? Is it in the S block, the D block, the P block, or the F block? That's the first most important thing, because it's always going to start out the same. You're always going to write the same stuff until you get to the very end, and where you stop is actually going to change what your answer is, because you're basically going to read like you're reading a book from the first element all the way to the last element. Hydrogen, helium, all these other ones. Everybody stay awake. I see some eyes getting sleepy there, so give you some not sunlight, but some light to help you stay awake. You're going to read this like a book from left to right until you get to your element that they're asking you about. That's where you're going to stop. So once you do a couple of these, you'll see you do 1s, 2s, 2p, 3s. You do these a lot because it's always the beginning. Where you stop is going to tell you what element you have, how many electrons it has. So what we're going to do real quick, I'm going to start to write some of this down on the board. And they'll probably show this on another slide, but I'm going to have it on the board so everybody can see it. This number, the first number is your energy level. So let me write that here. Energy level. The letter is your block of the periodic table. It tells you what area of the periodic table you're in. I'm just going to write block. This is the S block, the P block, the D block. That will tell you what part of the periodic table it's in. And then you will have an exponent up here. The exponents are literally how many electrons you have. So if you're not stopping yet, you're going to have the most electrons you can have in that actual block. So S block has 2 elements. It has 2 electrons. 2 is the most you can have in any S block. P block has 6 elements. There's 6 electrons. 6 is the highest number you can have for any P block. You can go lower if you're stopping, but you can't go above 6. Same thing, D has 10. You can't go above 10 for D. F has 14. You can't go above 14 for D. Or F, I mean. So this is your actual number of electrons. I think we'll see probably an example hopefully here pretty soon. But right here, actually, we can use this example. All right, I'm going to turn this off for a second so everybody can see it. They start off in the beginning. 1s. Where's 1s? It's the first row of the S block, including hydrogen and helium. And how many electrons do we have? 2 electrons. We have 2 atoms, hydrogen and helium. We have 2 electrons, 1 for each of them. Then you go to 2s. Lithium and beryllium. We have 2 elements. We have 2 electrons. It's 2s squared. So now we have 4 electrons total in these 2 sections. We keep going. 2p6. 1, 2, 3, 4, 5, 6. We have 1 electron for each element. You're just adding more protons, adding more electrons. We go all the way through that row. Then we go to what? The next row down. 3s squared. So that's going to be sodium and magnesium, and we have 1 electron on each of those. Then we go to 3p to the 6th power. So we're going to the second row in the P block. See, there's no D row yet, so we haven't gotten there yet. We're in the second row of the P block, aluminum through argon, and they go all the way through that because they give us 6. We're only going to have 2 more. We have 4s2. So now we're on our 4th row of the S block, potassium and calcium. So we know we've gone through those 2. And now we get to the end, 3d5. How many elements are in the D block? No, that's the F block. 10. There's 10 elements in the D block. Do we have 10 electrons here? No. So this is actually where we're going to stop, and we're going to figure out what element they're talking to us about. So we're going to start at the left of this top row of the D block, which is 3D, and we're going to count over, I think that's a 5 electrons or 5 elements. So what's the 5th element in that row? Manganese. Yeah, it looks almost the same as magnesium, but there's a weird N in there. Manganese is element number 25. So that is the element that this is describing. It tells you where all the electrons are in it and how many they have. If you add up these exponents, what's 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. 18 plus 2 is 20. And 20 plus 5 is what? 25. How many protons does manganese have? 25. And if it's a neutral atom, it'll have 25 electrons. So we literally just counted off all the electrons. We told ourselves what place they're in, what orbital they hold, and how many there are all the way up to our atom, which has 25 electrons. And we even included those last 5 in the 3D row. And so this is actually really important for knowing what your electrons are doing. Why do we do this? Why do we care? Because you don't want to just go into the lab and mix things and not know what you're going to make. If you know where all the electrons are at and what they're available to do, before you mix your chemicals in the lab, you can predict what you're going to create and know what you're going to get out and know whether it's going to be poisonous, whether it's going to be good, bad, or something that's useful to you. So for elements with larger numbers of electrons, we give you a different type of notation. It requires a lot of writing. Their example, that one was kind of short. If you went to like platinum down here at the bottom, you'd have a whole bunch of numbers written out. Platinum has 78 protons. You'd have to write out 78 different electron configuration or things for 78 electrons. So what we do, we go to the noble gas. And they did the same thing, 3d6. But instead of doing every single row, they start at the last row. So what row is 3d on? Yeah, it's in the fourth row. So 3d, the d's are a little bit off. It's in the fourth row. So we did 1s squared, 2s squared, 2p to the 6, 3s squared, 3p to the 6, 4s squared, and then 3d to the 5th power. That's a lot to write out sometimes. That one's not too bad. You'll have to write out worse than that. But this is kind of a long one. It'd be easier if we just had to do that last row, because if it's always the same, if you're always writing the 1s, the 2s, the 2p, you kind of get that. So let's start on that row with 4s. So 4s squared, 3d to the 5th. That'd be pretty easy, right? But we want to make sure that everybody knows that we're on the right row. And so we're going to add in the noble gas, the last noble gas that we crossed. So where are the noble gases? Use your key here. Where are the noble gases? They're all the way on the right side. They're to the very right, that last column. So helium, neon, argon, krypton, xenon, radon, and this last one, which we'll never use. But those are all your noble gases. You're going to go to the last noble gas you crossed. So did we get to the noble gas in row 4? No, we stopped there. So the last one we crossed was in row 3, right? And which is what? Argon. So that's what we're going to put here. Argon in square brackets. That's how we shorten this up. This one's not too shortened, but we took all of this. Basically, if we stopped right here, 3p6, what element will we be talking about? Argon. And so we just shorten all of that and say, hey, this is argon. We're going to start from argon, and we go here. So this is your normal one. This is called ground state. This is your shortened one. This is your noble gas configuration. So look out for that because if they ask you for the noble gas configuration, you don't want to waste all your time writing all this out if you don't have to. So make sure that you're reading the questions and seeing what they're asking you for. Because if you get to do the short one, it'll be a lot better, and you don't want to miss that opportunity. Is everybody really excited about this? I can tell. I can really tell. So let's see. You can see they have that down here, the noble gas configuration, just like I did on the board. Okay, so the end of each electron configuration of each element contains the valence electrons. How many electrons they have? I've kind of already told you that. So these are your actual electrons. If you add up all of your exponents, that adds up to the same number of electrons that atom has, and it should be equal to the same number of protons that atom has, as long as it's neutral. Wow, we reached the end. I didn't know that we would ever reach the end. So go ahead and open up your Chromebooks, and let's take a look at some of these problems. I will actually see if I can pull a couple up and show you a couple, just to get you started. It's only 10 questions, but I want you to take your time on them because you're going to see this on the test for sure. And we won't do that one. They got colors. Make sure you go to Google Classroom and open up this study sheet. That's going to help you with those shapes and the different colors. Okay, so like this one. Get the full electron configuration. Do not use the noble gas abbreviation. And then name the element. So they want to know what element they have here. You're basically going to write this out just like I did on the board. You're counting, instead of electrons this time, you're counting arrows. So in the first one, I have 1s. How many arrows are in there? 2. So 1s squared. And the next one, I have 2s squared. And the third one, I have 2p to the 6th. And notice you're going the same route here. It's always the same path. Where I stop is going to change what element that I have. And actually, is this the one that I've already done? Yeah. So if I go through this, where do I end here? What's the last thing I end with? 3D to the fifth. Yeah, sorry, I didn't mean to cut you off. 3D to the fifth. And so what element was that? Manganese. Manganese, which is a weird name. But it's manganese. So you just need to write it out like we already did and tell them what element it is. It's manganese. If it's neutral, it has the same number of protons as electrons. So you should have 25. But we'll go ahead and finish this anyways. 3s2, 3p to the sixth, 4s2, 3d to the fifth power, and that's where we stop. And so remember, you're literally just counting electrons as you move through the periodic table to try to figure out what element you're stopping at. Because you're always starting at hydrogen, you're always moving like you're reading a book from left to right, and then when your electrons run out, that's when you stop. And so this is actually going to be one that helps you out a little bit in kind of understanding. They give you 4 different elements. You need to figure out which answer goes with which. And notice they give you 6 answers. So it's not just going to be like, just stick them in there and I'll figure it out. If you don't know what you're doing, you're not going to get to the end. So look for the sections. Look for how many electrons you have. Maybe add up the total number of exponents and see how many electrons you would have and how many protons you would have. And that might help you get to the end. I don't know. Maybe I'll record a different one this in the next period because I feel like that maybe wasn't my best lecture ever. But it's hard stuff. It's hard stuff. It's not easy to talk about. So if you see this on Google and you're having questions, let me know and send me an email, preferably during the middle of the day, and I'll be able to get back to you before class lets out. And thanks and have a nice day.